Hello. So, in this module we are going to talk about macroscopic balancing or integral analysis. During the start of this course in first few lectures we talked about the approaches that we can take to solve problems of fluid mechanics. So, we looked at main three approaches that one can take to solve fluid mechanics problems. The number one was dimensional analysis. So, where we can list down all the parameters on which the flow depends, and then using dimensional analysis we can find out the relevant non-dimensional groups and identify the independent parameters on which a dependent parameter will depend on. Now, it can be used to design experiments or to give directions to our experiments. The next approach, so the dimensional analysis approach is a very primitive approach, but it is very useful to give or to get some insight in the physics of the problem. But we cannot get much quantitative analysis about the problem from the dimensional analysis. The next approach we talk about is macroscopic analysis or integral analysis. So, in this approach what we will be looking at that on a macroscopic scale, what are the forces or what is the energy exchange through a control volume. So, when we identify the system or when we identify the flow domain, we can find out using macroscopic balances the force being exerted on a particular body or the force exerted by the fluid on a beam, on the pillar of a bridge or on a car, etc. What we will be able to get is the integral of this force. We will not be able to get the distribution of the flow field or the distribution of the force on the surface, and that can be obtained using differential analysis. So, what we are going to talk about is macroscopic balances in this module, or we also know it as integral analysis. Now, as we discussed in the introduction that the fluid behavior can be analyzed using Lagrangian approach or Eulerian approach. So, Lagrangian approach is that when we identify a fluid particle and move with it. So, we are looking at the motion of a fluid particle or motion of a number of fluid particle, individual fluid particle. When we are following those particles and looking at their velocity field, then that approach is Lagrangian approach. Now, in solid mechanics, when we are analyzing the motion of rigid bodies, we usually use this approach. So, for example, we are analyzing the motion of a car, analyzing the motion of an aeroplane or motion of a rocket. We follow their path from Earth all the way to Mars, for example, if we are talking about a rocket. However, when we are looking at a fluid, we are generally interested, let us say if we talk about rocket, and when we are analyzing the motion of a rocket, we of course need the force that the rocket will experience because of the fluid surrounding this rocket. So, we are interested in the fluid motion surrounding in a region surrounding this rocket. So, our region of interest is a particular volume surrounding the rocket. We are not interested in the motion of a fluid particle that was surrounding the rocket at the earth. We will be looking at the motion of the fluid particles that may be present at any time. We will be looking at the motion of fluid particle that will be present around this rocket at any particular time. So, that approach what we call Eulerian approach, that we are looking at the motion of fluid in a particular region of interest, and the fluid can come and fluid can go out of it. So, using these two approaches, Lagrangian approach and Eulerian approach, we can solve fluid mechanics problem, but as I said, generally we solve conventionally all the fluid mechanics book or most of the theory that has been developed for solving fluid mechanics problem is developed for Eulerian approach, because that suits well for fluid mechanics problems from application point of view as well as from analysis point of view. So, to do this, first we need to look at what is system and control volume. So, what we define in system, when we talk about Lagrangian approach, we are talking about the motion of a fluid particle or a group of fluid particles. So, the system is basically a fixed mass, and this mass or this system may be rigid or a deformable mass, but there is no transfer of mass from the boundary of this system. So, system is a motion of it can be an individual fluid particle or group of particle, and that is what we analyze when we talk about Lagrangian motion. So, most of the laws that we talk about, because that is what we have been using for rigid body analysis, we take a system, we take a car, we take an aeroplane, or for example, we take a balloon which is a deformable body, or piston cylinder system. There again we have a change in the volume, but the mass inside the system is fixed. So, when we talk about rigid body motion, we generally use systems approach. So, all the laws that we have been studying applicable for rigid body motion, because they are laws of mechanics and they are applicable for any matter, they will also be applicable for fluids. Now, we want to use those laws for fluid mechanics or analysis of fluid motion. However, those laws has been written or has been developed using a systems approach or using Lagrangian approach, where the system is fixed. Okay. Now, in the fluid mechanics, we use control volume approach, or we look at a fixed region in space and analyze the fluid motion. So, the fixed region is in space is what we call control volume. So, this control volume, in this we take a particular region of space, and the fluid can come in and go out of this fluid region of this specified region. Now, this region, it can be fixed or it can be moving. The region that we talk about, or this control volume, can be rigid. We can have a fixed boundaries of this control volume, or this can be deformable. So, we should remember this control volume is an imaginary volume that we talk about. So, it is not necessary that it will always be a enclosed volume where we will have some doors and windows etc., from which the flow can come in or go out. When we do when we analyze the problem, most of the time we will see that the control volume is an imaginary volume, and depending on the problem we might need to assume that the this control volume is fixed, or it is moving with a constant speed, or it is moving with or it is accelerating, or the control volume is fixed or its boundaries are fixed, or control volume may also be having flexible boundaries or moving boundaries. Okay. So, the boundaries of this control volume, we will call this the boundaries of the control volume as control surface. So, in today's lecture, what we are going to look at, we already know what are the laws of mechanics applicable in systems approach or in the Lagrangian approach, and we will try to relate these or try to identify that how we can write down, knowing the laws for a systems approach, how we can relate them with an Eulerian approach. So, how can we write down these laws for an Eulerian approach and use it for fluid mechanics problem? That is what is going to be the crux of this module in macroscopic balances. But before we do that, we will derive a general relationship which can relate the formulations or the laws of mechanics with system formulation to control volume formulation. So, before we do that, let us look at the main laws of mechanics. The main laws of mechanics that we will be using or that we need to use is, the first one is conservation of mass. So, this we might not be using very frequently to solve problems in rigid body mechanics, because sometimes it is implicitly assumed that in a rigid body the mass is of course constant, but in fluid mechanics we need to look at this. So, the first law is that in a system where the number of fluid particles is a constant, so the mass remains constant. And as we will see after few minutes, that all the things that we are looking at, we need to write in terms of a rate. So, we will write that mass is constant, or in terms of rate, what we can write that the rate of change of mass of the system, where capital M is mass of the system, is equal to 0, that is mass is constant. So, mass does not change with time. We can also write this in terms of density and volumes, because we will frequently encounter the velocity vector v and v volume. So, to differentiate this, we will use that capital V as velocity vector and a horizontal line cutting across V we will use for as a symbol for volume. Okay. So, the mass we know that is density into volume. So, if we have a small elemental volume dV, then the mass in that will be rho into dV. If rho is changing or if rho is not constant throughout the volume, then we will need to integrate this over the control volume. So, d integral over the control volume rho dV by dt will be a differential form where we can consider the space dependent density of in the system. So, that is basically the conservation of mass. Now, the next important law for mechanics is conservation of momentum. We can have a linear momentum and angular momentum, but in this course we are going to restrict ourselves for conservation of linear momentum only. So, conservation of linear momentum is basically what we know popularly as Newton's second law of motion, which states we already know that F is equal to m a, popularly F is equal to m a is the expression for Newton's second law of motion. So, in words we can say that for a system moving with or moving relative to an inertial frame of reference. So, we will many times encounter this term inertial frame of reference. So, to remind ourselves that what is inertial frame of reference mean that the frame of reference is either stationary or it is moving with a constant speed or constant velocity. It is non accelerating. So, when the frame of reference or our coordinate system, if it accelerates, then it will be a non-inertial frame of reference. So, Newton's second law states that for a system moving relative to an inertial frame of reference, sum of all forces that is acting on the system, that will be equal to rate of change of linear momentum of the system. So, linear momentum P is equal to mass of the system into velocity. So, F vector F is equal to dP over dt. So, the rate of change of momentum of the system, that is equal to the force applied on the system. In when you consider that in terms of differential quantities or in a differential volume dV, if rho is the density and v is the velocity vector, then force is equal to dP by dt, that will be equal to d by dt in the integral form, integral over the system volume m into v, where or dm into v, v is the velocity vector and dm is rho dv. So, that is conservation of momentum. And the third law, which is conservation of energy. So, when we talk about incompressible flows, and if the flow is isothermal, we do not need conservation of energy until we are talking about problems related with heat transfer. But when we talk about compressible flows, so in compressible flows the density is not a constant, and we need to relate density with the properties of the fluids. So, we need to use a law which can relate rho, which is density of the fluid, with the system properties or the fluid properties such as pressure and temperature. So, the simplest law relating pressure and temperature with density is ideal gas law. Rho is equal to P m by R T for an ideal gas, where m is the molecular mass of the gas. So, if the flow is compressible, then we need to solve for energy equation, because then we need temperature, and the temperature field may be changing because the velocities are high. So, we need to essentially solve conservation of energy always, but for incompressible flow we may need to solve conservation of energy only when there is heat transfer involved, or the flow is not isothermal. Okay. So, the conservation of energy is basically given by first law of thermodynamics, which states that the change in energy of a system, that is equal to delta Q minus delta W. So, delta Q is heat supplied to the system and delta W is the work done by the system. Now, because the other two laws we have written in rate form, and when we talk about the flow of fluid, it will be when the fluid comes in or goes out, the energy will be coming in and going out. So, in place of the what is the energy coming in, we will be interested in what is the energy coming in time delta t, or in other words we will be talking about the energy coming in per unit time, work done per unit time, and the change in energy in per unit time. So, we will be talking about in terms of rates. So, the conservation of energy will be in terms of rates, that dE by dt of system, that is equal to Q or rate of heat input to the system minus work done by the system on the surroundings. So, when we talk about systems, we always have surroundings in it, that anything that is around the system, because when the system, the mass is fixed. So, around the system what is present is what we call surroundings. So, system interacts with surroundings, and that interaction results in terms of forces that we saw in Newton's second law of motion or conservation of linear momentum, and the here we are looking at the energy exchanges with the surroundings for a system. So, this capital E or the energy or total energy of the system will be integral small e, where E is the specific energy and dm is of course the differential mass of the small volume, and this energy will be sum of specific internal energy u plus v square by 2, where v is speed and g z, where z is the height from a reference position. So, it is sum of the total energy is sum of specific internal energy, kinetic energy and the potential energy. All of these are of course in terms of specific energy. So, the units for all of these will be joule per kg. Now, just to remind ourselves that the sign of q dot, which is that when heat is being added to the system, then it will be positive, and sign of w dot when work is being done by the system. So, this we can understand by looking at this expression itself, that rate of change of energy will be positive. So, energy dE by dt will be positive. That means, the system will get energy if there is some energy being supplied from outside. So, if heat is being added to the system from the surroundings, if the system gets some heat, then only delta E will be positive. So, q dot is positive or heat being supplied is positive when heat is being added to the system. W dot will be positive because we have a negative sign in this equation. So, W dot will be positive when the system spends some energy to do work. So, when somebody does work or when the system does work, it needs to spend energy. So, because we have a minus sign here, so there will be a decrease in the energy of the system when work is being done by the system. So, sign of W dot will be positive. Now, these signs depends on what form of equation do we choose. So, it is always important when we are looking at the any form of conservation of energy or first law of thermodynamics, we should always remember that what sign we are going to use for Q and W. Okay. So, if we look at all three of these equations, conservation of energy, conservation of momentum and conservation of mass, all of those had dm by dt, which is rate of change of mass, dp by dt or dmb by dt, which is rate of change of momentum, and dE by dt, which is rate of change of energy. So, all these were rate of change of a property of the system. Okay. So, we will be talking about now, or in this lecture, what we are going to do is how do you relate rate of change of property in a system in a general sense. This property can be mass, this property can be momentum, or this property can be energy, or for that matter it can also be angular momentum or entropy of the system, and we will relate it with the rate of change of this property in a control volume. Okay. So, before we do that, we will just define a general property, which is an extensive property N, and then corresponding to each extensive property, we will also define an intensive property, which is extensive property per unit mass. So, To remind ourselves what is extensive and intensive property, the properties of the system or properties of a material which depend on the quantity or on the size of the system or the volume of the system that is present, that those properties are called extensive properties. So, for example, the temperature of a system does not depend on what is the size of the system or what is the mass of the system. So, temperature is an intensive property. Similarly, density is an intensive property because it does not depend that how much fluid is present or how much a particular matter is present, whereas the volume or the momentum, they are all extensive property because they depend on the mass of the system. So, for each extensive property, all the three properties that we talked about in the three laws, mass, linear momentum and energy, M, P and capital E, they are extensive properties, but corresponding to each of these, if we divide them by mass, we can find an intensive property. So, we define in general an extensive property which we call N, and the corresponding intensive property is what is eta, which is N by M, or in differential terms we can define that capital N of system is equal to integral over the system eta dm, okay, where m is of course mass, or if we write dm in terms of rho dV, then this will be equal to integral over the volume of the system rho eta dV. So, let us just see, if we are talking about mass of the system, then eta will be of course mass divided by mass, which is 1. If we are talking about momentum of the system, which will be a vector quantity. So, momentum is equal to capital N, extensive property is momentum P, then corresponding intensive property eta will be P by m, which is well basically velocity vector. And if N is equal to E, which is total energy of the system, then the corresponding intensive property, as we also saw in the previous slide, that eta will be specific energy small e. Okay. So, we will when we will use the principle that we derived today, or what we call Reynolds transport theorem, we can use or we can substitute E and E for N and eta, or P and V for N and eta, or M and 1 for N and eta, depending on we are using energy conservation, momentum conservation or mass conservation. Okay. So, let us define first a control volume. Okay. So, if we consider a system, or if we consider a small control volume fixed in space. So, in this picture what we see is a control volume which is shown by dotted lines. So, this is our control volume as is written here, that it is shown by dotted lines. Now, at time t naught, the fluid surrounded by this control volume is what we consider as system. So, if we consider a system which is shown inside this control volume, this is our system. So, the system which going to move if the fluid is moving, but our control volume, we consider the control volume is fixed. Okay. Now, because the flow is free, it can come in and go out of this control volume. So, the surface of this control volume, all this the dotted line is what we call control surface CS. Okay. Now, the flow can come in or it can go out. So, flow may come in normal to the control surface, or it may be coming in at an angle to the normal to the control surface. Okay. And flow may leave the control volume either normal to it or at an angle to it, or the flow might be moving along the control surface. So, the streamline, this line might be a streamline, or this might be a wall. So, all possibilities can happen, that the flow may come in through the control surface, or the control surface may be coinciding with a streamline. So, we know that the flow cannot cross a streamline. So, again there will be no flow through the control surface, and it may have wall. So, generally because we are talking about flow of fluid, so through this control volume there will always be some inflow coming in and some flow might be going out, or you might have only flow coming in or flow might be going out. But generally when we solve problems, there will be at least one of these flows, the flow is coming in or flow is going out, because then only we are looking at the motion of fluid. So, when we talk about the flow coming in or going out, so the net flow rate will be V dot N dA. If we take a small area dA in this control surface, and the unit normal to this area dA is n cap, okay, and there is an angle between the velocity vector and the unit normal. The flow is going out, then the volumetric flow through this area dA will be V dot N dA, or that will be V dA cos theta. Okay. So, that will be the flow that is going out of the system. Similarly, we can use, if the flow is coming in through the system, there of course, the velocity vector and the outward normal. So, conventionally when we take a normal to the surface or normal to the control surface, we always take outward normal. So, when the flow is going out, V dot dA will be positive, but when the flow is coming in, it will be negative. Okay. So, through this or V dot dA vector or V dot N dA, we can obtain the flow rate, volumetric flow rate, and if we multiply it with density, we will get mass flow rate. So, we have this control volume and system coinciding at time t naught. So, after time delta t, the system moves to a different position, as we can see here. The system is colored in blue, and the control volume is fixed as it was at time t naught. So, it remains in the same location. Now, we consider the motion of a particular intensive property n, or what has happened to n when the system has moved from location from the control volume from this position to this position. So, to do this, we have divided the system at time t naught plus delta t. In this figure, we identify 3 regions. So, let us look at this. Region 1 is, that is part of the control volume, but the system has moved through it, okay, and we try to hatch it with a kind of horizontal lines. System the region 2 is, which is the intersection of the two, it is part of the system still, and it is also inside the control volume, and region 3 is what has moved out of the control volume, but it is part of the system still. Okay. So, we consider these three regions 1, 2 and 3. What we need to find is basically the rate of change of intensive property of the system. So, if we write the rate of change of n in system dn by dt of system from the fundamental definition of derivative. So, we can write that in the limit delta t tending to 0, dn by dt will be equal to ns at t naught plus delta t, which is the intensive property n inside the system at t naught plus delta t minus intensive property n inside the system at time t naught divided by delta t. So, that is dn by dt. Now, we can try to see these two terms ns t naught plus delta t and ns t naught from what we saw and see in these figures in terms of what is there inside region 1, 2 and 3 or control 1. So, we see that ns t naught or the intensive property in the system at time t naught will be equal to the intensive property n inside the control volume at time t naught, because at time t naught the system and control volume coincide. So, the intensive property in the two will be same. Now, let us look at the intensive property inside the system at time t naught plus delta t. So, that we can see that this is equal to what is there inside the system n 2 and 3. So, n 2 plus n 3 at time t naught plus delta t. Now, n 2 what we can see here is n 2 is n inside the control volume at time t naught plus delta t minus n inside the region 2, because region 2 is still inside the control volume. So, n 2 that will be n 1. So, sorry, now let us do it again. So, n 2 is equal to inside the control volume n c v at time t naught plus delta t. If we subtract n 1 inside the control volume at time t naught plus delta t, then we can write that n 2 is equal to n c v minus n 1 both at time t naught plus delta t, plus of course n 3 remains same. Okay. So, we can substitute the two n s t naught plus delta t and n s t naught in this formula. So, we get d n by dt of the system, that is equal to limit delta t tends to 0. We can substitute n as t naught plus delta t, that will be n inside the control volume at time t naught plus delta t minus n 1 inside the control volume or minus n 1 at t naught plus delta t plus n 3 t naught plus delta t. So, n 1, n 3 and n c v, they are all at time t naught plus delta t in these respective regions, region 1, region 3 or inside the control volume. Minus in place of n s t naught, what we write is n c v t naught divided by time delta t. So, now we can rearrange and write it again. So, dn by dt of system, that will be equal to in the limit delta t tends to 0, we can take n c v, which is at time t naught plus delta t minus n c v at time t naught. So, we can take those together divided by delta t, and we can see that this will give us dn by dt inside the control volume. Okay. Plus we have two more terms, which is limit delta t tends to 0 n 3 t naught plus delta t divided by delta t minus limit delta t tends to 0 n 1 t naught plus delta t divided by delta t. Now, if we look at what is n 3 and n 1. So, n 3 is the region which has gone out of the control volume and N1 is the region which has come inside the control volume. So, basically N represents the intensive property. So, the intensive property that has come inside the control volume is N1, and intensive property that has gone out of the control volume in time delta t is N3. So, let us simplify this and we can write the first term is equal to d by dt of NCV. So, the rate of change of intensive property in the control volume. Now, let us look at this term. So, if we take a small sub region as shown here, okay, in the red, and the volume of this sub region is dV, if we say. So, that basically represents that in this small volume it represents what is the flow rate or what fluid has gone. So, the volumetric flow rate will be V dot dA, as we discussed just now, that if there is an if V and dA they are not collinear or they are not parallel to each other, then the volumetric flow rate that comes out through this area dV will be equal to V dot dA. So, because this is the flow that has gone out of the control volume in time delta t. So, through this area dA, the flow that has gone out, that will be V dot dA into delta t. So, in time delta t, V dot dA delta t is the volume of the fluid that has gone out. Now, what will be the intensive property that has gone out through this? dN through in region 3 T naught plus delta t, that will be equal to eta rho multiplied by the dV. So, dV we know V dot dA delta t. So, we can substitute this in place of dN3 or in terms of integral. So, if we integrate over this entire boundary, what we call control surface 3, that is the boundary that intersects between the control volume and the system. So, over this control surface 3, eta rho V dot dA delta t divided by delta t, and delta t is a small time which is constant or independent of this control surface boundary. So, delta t will cancel out and what we get is this limit delta t tends to 0, intensive property in region 3 at time t naught plus delta t divided by delta t, that is equal to integral over control surface eta rho V dot dA. So, that basically represents the intensive property that has gone out of the control volume through this control surface. So, that is the intensive property that has gone out of the control volume. Now, similarly, we do the same analysis for region 1. For region 1, the only difference that is going to come in, that in this case the fluid is going to come inside the control volume, right. So, if we consider a small region of in region 1, then the flow rate here, because the outward normal and the velocity vectors they are in the opposite direction. So, the flow rate that will be coming in will be minus V dot dA. So, doing the same analysis, but with a minus sign, because the flow is coming inside the control volume. So, we will get limit delta t tends to 0 N1 at time t naught plus delta t, that is the intensive property in region 1 at time t naught plus delta t, that is what has come in time delta t inside the system. So, that will be equal to minus integral over the control surface 1, which is this boundary, that is the intersection of region 1 and control volume. So, that you will have that is equal to eta rho v dot d A. So, this is the surface C S 1 through which the fluid comes in. Now, we substitute this. So, there is negative sign, this negative sign is because velocity vectors and area normal, they are in the opposite directions and their dot product will be negative. So, we add a negative sign there. So, if we substitute all this, then our equation becomes that rate of change of n inside the system, that is equal to rate of change of n inside the control volume plus the flow that is coming in C S through the control surface C S 3, the intersection of control volume and region 3 eta rho v dot d A plus integral over control surface 1 eta rho v dot d A through control surface 1. Now, because we have taken the negative sign into account while deriving this, we can combine these two. So, on combining we can write the general equation that d n by d t of system, that will be equal to d n C b by d t, the rate of change of intensive property inside the control volume, that is equal to the net outflow from the control volume. So, that is that the rate of change of extensive property n, that is equal to the rate of change of n in control volume plus rate which the property n exits the surface of the control volume. If it is coming in, then we have to take into the negative sign of v into account, and that will be taken care of by the sign of outward normal and the velocity vector. So, if we look at this is a mathematical expression, and that will be very useful when we solve problems and identify that what mass, what is the momentum or energy that is coming in and going out of the system. But if we look at this system, this is a very simple equation which tells us that inside a control volume, the rate of change of a intensive property in the control volume is equal to rate of change of extensive property inside the system minus that has gone out of the controls through the control surface of this control volume. Okay. So, we will stop here, and in the subsequent lectures we will look at the application of this equation, which is known as Reynolds transport theorem. So, this is what we call RTT commonly, or Reynolds transport theorem, which will be used for converting the conservation of mass, conservation of momentum and conservation of energy formulations from a system formulation to a control volume formulation. So, in the subsequent lectures we will look at that how we will do that and solve some problems. Okay, we will stop here. Thank you.